Since the dawn of human civilization, we have cast our gaze toward the brilliant river of stars above. Those countless distant suns, like unknown worlds, have perpetually beckoned to us. From the ancient feats of crossing vast oceans in wooden vessels to the modern journey of rockets carrying us to the moon, the pace of human exploration has never ceased. However, when we speak of crossing the interstellar void to reach another star system, a seemingly insurmountable barrier stands before us. Even Proxima Centauri, the closest star to our solar system, would take tens of thousands of years to reach at the speed of our most advanced space probes. Such a timescale is equivalent to eternity for the small and brief span of human life. We long to leave our cradle, yet we are ruthlessly confined to the neighborhood of Earth by the vastness of the cosmos. Thus, a grand dream was born, a magnificent vision that transcends existing physical limits, the warp drive. This story is long, so let us take it into our dreams. Before we begin, do not forget to like and share. In the Grand Hall of Physics, the speed of light is solemnly dictated as the ultimate speed limit for any object with rest mass in the universe. This is not a simple technical bottleneck but a cornerstone of the fundamental laws that constitute our universe. Einstein's theory of relativity tells us that as an object approaches the speed of light, its mass increases dramatically, and the energy required to accelerate it climbs toward infinity. This means that no matter how powerful our thrusters become, we can never truly reach the speed of light. This impassable red line firmly binds us to the small corner of the solar system. To achieve true interstellar travel, we must find a completely new path, a clever method that does not attempt to accelerate to the speed of light but fundamentally bypasses the speed limit altogether. Like the origins of many great scientific ideas, the warp drive began as a spark of imagination from science fiction writers. In the 1960s, a television series called Star Trek brought the concept of warp into the public eye. The starships in the show used warp engines to make travel to distant galaxies a common occurrence. This setting, which achieved faster than light travel without violating the laws of physics, quickly ignited the imagination of countless people. It was no longer just a romantic fantasy but became a possibility. Once the seeds of science fiction take root in the soil of reality, they attract the most creative scientists to dedicate themselves to research, attempting to turn this impossible dream into reality. It was not until 1994 that Mexican physicist Miguel Alcubierre, inspired by science fiction, first introduced the concept of warp into the rigorous academic field. In a paper, he proposed a revolutionary mathematical model, a scheme using the equations of Einstein's general relativity to achieve faster than light travel. His theory, known as the Alcubierre metric, described a concept of creating a bubble of distorted space-time to carry a spacecraft without violating local physical laws. This paper was like a bolt of lightning illuminating the theoretical path to interstellar travel. For the first time, it made people realize that the warp drive might not be pure fantasy but a physical problem worthy of serious exploration. The core idea of the Alcubierre warp drive is that the ship itself does not move at high speed through space-time. Instead, it remains stationary inside a space-time bubble distorted in a special way. In front of this bubble, space-time is extremely compressed, while behind the bubble, space-time is extremely expanded. Imagine standing on a flat tablecloth. Someone pulls the cloth from behind you while shrinking it in front of you. You have not moved, but the cloth beneath your feet is moving forward at high speed, carrying you to a distant place. The warp drive utilizes this plasticity of space-time by creating such a wave to carry the ship beyond the speed of light. Inside the ship, space-time remains flat, meaning the vessel and everything on board experience no enormous acceleration forces. Passengers could complete interstellar journeys in comfort. However, as beautiful as Alcubierre's theory was, it soon encountered a massive obstacle. According to his mathematical model, creating such a space-time bubble requires placing a substance with exotic physical properties around the ship. This substance must possess negative energy density, meaning its energy value is less than zero. In our daily experience, all known matter and energy possess positive energy. Negative energy matter is a concept that does not exist in classical physics and is only mentioned in some fringe theories of quantum physics. Whether negative energy matter exists and how to manufacture and stabilize it in large quantities became the greatest challenge for warp drive theory, moving from a mathematical model to engineering reality. Beyond the harsh requirements for negative energy matter, the original Alcubierre metric faced another desperate problem: enormous energy consumption. Early calculations indicated that to create a warp bubble large enough, the negative energy required would be equivalent to the mass of the entire planet Jupiter. This is an astronomical figure far beyond any form of energy human civilization can imagine. Although later physicists significantly reduced the energy requirements by modifying the model, some even suggesting that negative energy equivalent to the mass of a solar system planet might suffice, this demand remains out of reach for our current level of technology. This series of severe challenges made the dream of the warp drive seem to return to the realm of pure science fiction. But this did not cause scientists to give up. Over the past few decades, physicists have been working hard to find new solutions, trying to make the warp drive more realistic without violating the laws of physics. They explored new space-time metrics, looked for alternatives to negative energy matter, or studied how to manipulate space-time in clever ways. Some turned to quantum physics, trying to find the possibility of creating tiny negative energy regions within quantum vacuum fluctuations. Others tried to shrink the scale of the warp bubble to the subatomic level to reduce energy needs. Although there is currently no verifiable experimental plan, this ongoing research proves humanity's desire for interstellar travel and the eternal exploration of cosmic mysteries. To solve these puzzles, we must look back at Einstein's special relativity. The core of this theory is built upon two revolutionary basic assumptions: physical laws are the same in all inertial frames, and the speed of light in a vacuum is a constant value in any inertial frame, independent of the motion of the light source. These two seemingly simple premises completely overturned human perception of time and space. Special relativity revealed that time and space are not absolute and unchanging. When an object moves at extremely high speeds, the time it experiences is slower than that of a stationary observer, a phenomenon known as time dilation. Simultaneously, the length of the object in the direction of motion contracts. Einstein's theory tightly linked time and space into an inseparable four-dimensional whole called space-time. In this structure, the speed of light is no longer just a speed, it is the ultimate bridge connecting energy and mass and the absolute upper limit for any massive object. Because an object's mass increases with speed, the energy required as it approaches light speed tends toward infinity. This universal law became an impassable wall for the dream of interstellar travel. However, Einstein's revolution did not stop there. He soon realized that special relativity could only describe objects in uniform motion and could not explain gravity. To include gravity, he spent 10 years developing general relativity. He proposed that gravity is not a mysterious force but the curvature of space-time itself caused by mass and energy. To make this abstract concept easier to understand, Einstein used a vivid analogy. Imagine a stretched rubber sheet representing flat space-time. If we place a bowling ball on it, its mass causes the sheet to sag, forming a curved region. Now, if we roll a marble nearby, it will not travel in a straight line but will follow the curved track created by the bowling ball, as if attracted by an invisible force. In this analogy, the bowling ball represents a massive celestial body like the Sun, and the marble represents Earth. The Sun's mass curves the space-time around it, and Earth moves along this curved path. The gravity we feel is merely a macroscopic manifestation of space-time curvature. General relativity provides the core physical foundation for the warp drive. If gravity is the curvature of space-time, then a natural question arises: can we artificially curve and manipulate space-time to achieve our desired travel effects? Alcubierre's vision is based on this bold assumption. His idea is that we do not have to force the ship itself to move faster than light through space-time, as that is forbidden. Instead, we use a massive energy field to warp the space-time around the ship. By compressing space-time in front and stretching it behind, the ship is pushed by a massive surface wave. It remains stationary in local flat space-time while the entire bubble moves forward at superluminal speeds. This does not violate the universal speed limit because the ship is not moving faster than light relative to its immediate surroundings, it is merely riding a space-time wave. This is like a person on an escalator who is carried quickly to another place without running. Yet, this hopeful blueprint met the obstacle of negative energy. Negative energy is a highly counterintuitive concept where energy density is less than zero. While quantum mechanics features the Casimir effect which can produce tiny amounts of negative energy, the scale is far too small to drive a warp engine. This challenge led many to doubt the physical feasibility of the theory. Facing this, physicists began to optimize the model. They found that by changing the shape of the warp bubble from a perfect sphere to a torus or ring shape, the negative energy required could be drastically reduced, perhaps to the mass of a large cargo ship. While still astronomical, it is a significant step forward. Other radical explorations look toward dark energy, the mysterious force driving the expansion of the universe. Dark energy possesses negative pressure, which creates a repulsive force that pushes space-time outward, matching the physical needs for stretching space-time behind a warp bubble. If we could manipulate dark energy, we might bypass the need to manufacture negative energy. Furthermore, the study of the quantum vacuum offers hope. The vacuum is full of energy fluctuations that might produce tiny negative energy regions. If these effects could be scaled up, the dream could move from the macro universe to the micro world. Parallel to this is the theory of wormholes, tunnels connecting different regions of space-time. Like warp drives, wormholes require exotic matter to stay open. These theories prove that within the framework of general relativity, faster than light travel is not impossible, it simply requires a deeper understanding of the nature of space-time. In the vacuum of space, energy constantly fluctuates, giving birth to a myriad of virtual particles. Within the narrow gap between two metal plates, however, only those virtual particle waves whose wavelengths fit perfectly within that space can exist. Meanwhile, outside the plates, these waves can manifest freely. This creates an energy differential where the total energy outside exceeds the inner density, forming a pressure gradient and negative pressure that pulls the plates together. This phenomenon, though infinitesimal, provides us with a window into the enigmatic world of negative energy. Yet, scaling this microscopic effect to a magnitude capable of driving a warp engine requires a far deeper mastery of the quantum vacuum than we currently possess. It demands a level of precision in controlling and manipulating vacuum energy that far exceeds modern technological capabilities. Parallel to the concept of the warp drive is the theory of wormholes. A wormhole is another solution to Einstein's field equations, acting as a tunnel that bridges two distinct regions of space-time, potentially allowing for instantaneous travel across vast distances. Unlike the warp drive, which distorts the immediate surroundings of a vessel, a wormhole creates a shortcut through the cosmic fabric. However, Creating and maintaining a stable wormhole also necessitates negative energy. The entrance and exit of such a tunnel must be braced by exotic matter to prevent them from collapsing under intense gravitational forces. Thus, wormhole theory faces the same fundamental hurdles as the warp drive. Nevertheless, their existence in the framework of general relativity proves that superluminal travel is not a physical impossibility, but rather a challenge requiring a more profound understanding of space-time itself. While both concepts share similar obstacles, they represent two distinct philosophies of interstellar travel. One involves riding a wave of space-time, and the other involves taking a shortcut through it. Both offer boundless room for imagination. Further theoretical explorations have even proposed warp drive designs that do not rely on negative energy at all. The most prominent among these are modified theories of gravity, such as F of R gravity, which introduce extra terms into Einstein's equations. These modifications theoretically allow for faster-than-light travel without the need for exotic matter. While mathematically plausible, these theories face immense challenges. Their physical foundations lack experimental verification and may not accurately describe our actual universe. Furthermore, even if the theories are correct, translating them into a functional engineering project remains a monumental task. Yet, they suggest that the key to the stars might lie not in searching for exotic substances, but in gaining a deeper insight into the nature of gravity itself. When Alcubierre first introduced his warp drive theory, it was largely dismissed as a brilliant mathematical exercise rather than a viable engineering path. The sheer amount of negative energy required made it seem utterly unattainable. However, Harold White, an engineer at NASA, decided to take this dream from abstract equations into the laboratory. At the Johnson Space Center in Houston, White and his team established a specialized research group. Their goal was not to build a starship, but to find the smallest shred of evidence that a warp effect could exist. This marked a pivotal shift from theoretical deduction to experimental verification. White believed that even in the most unlikely places, one might find the key to the stars. White's contribution was a clever refinement of the original theory. He realized that a warp bubble did not necessarily need to be a perfect sphere. By studying Einstein's equations, he found that if the geometry was changed to a ring structure resembling a donut and made to oscillate rapidly in a two-dimensional plane, the energy requirements would plummet. His calculations suggested that the energy needed could drop from the mass of Jupiter to the mass of a single spacecraft. While still vast, this shifted the requirement from a cosmic scale to one that future human technology might realistically achieve. He referred to this as a space propulsion field, suggesting that the ring structure could be implemented using quantum phenomena related to the Casimir effect. To test this, the team developed the White-Jude warp field interferometer. This device used a split laser beam to detect the tiniest distortions in space-time. If one path of the laser experienced even a minuscule curvature, the resulting interference pattern would shift. The team placed a specialized capacitor, consisting of ceramic electrodes designed to mimic the ring-shaped warp bubble, within one of the paths. When energized with high voltage, they hoped it would generate a faint warp field. Initial reports of subtle interference shifts caused a global sensation, with headlines suggesting interstellar travel was imminent. However, the scientific community remained cautious. Critics pointed out that the experiment was conducted in a noisy environment where temperature changes or passing vehicles could easily cause identical shifts. Since the results could not be independently replicated, a cornerstone of the scientific method, the findings remained controversial. Despite the skepticism, White's work was significant because it moved the warp drive out of the realm of science fiction and onto the laboratory bench. It proved that the concept could be tested with precision instruments. Since then, Other physicists have proposed even more complex experiments, ranging from high-energy particle collisions in the Large Hadron Collider to the use of superconductors and powerful magnetic fields. Each attempt, whether a breakthrough or a failure, provides invaluable experience. This journey is like a long treasure hunt. We do not yet know where the prize is hidden, but every step deepens our understanding of the universe. If the hurdles of warp drive physics are eventually overcome, and humanity builds the first vessel capable of curving space-time, it will be more than a technical feat. It will redefine our place in the cosmos. This would be the greatest migration since humanity first walked out of Africa. Earth would no longer be our only home, and the solar system would no longer be our final frontier. Distant stars would become accessible destinations. We would no longer be trapped in a single planetary gravity well, allowing us to spread the seeds of civilization across the Milky Way, ensuring our survival against any cosmic catastrophe. The warp drive would grant humanity true freedom, a freedom that transcends the speed of light. This technology would trigger an unprecedented social and economic revolution. Traditional notions of geography and distance would vanish. New interstellar trade routes would open, and rare cosmic resources would become available. The mastery of warp technology would likely lead to a total redistribution of wealth and power, as those who control the stars control the future. This could spark a new space race, with nations and corporations competing for resources, highlighting the urgent need for a fair interstellar order. Beyond economics, we would face profound ethical questions. How should we treat simple life forms found on other planets? How would we interact with other intelligent civilizations? These questions will test the limits of human wisdom and morality. The cultural impact would be equally transformative. Interstellar travel would blend diverse earthly cultures with new ideas and art from distant star systems. Our collective consciousness would expand from a planetary perspective to a multidimensional cosmic view. Our understanding of life's origins and the definition of ourselves would change completely. Ancient philosophies would gain new meaning, and space adventure would become the central theme of human culture. The warp drive acts as a mirror, reflecting both our courage and our flaws. It is a neutral technology that could create a peaceful federation or ignite a cosmic war. Its ultimate fate depends on us. The true challenge is not building a ship that exceeds the speed of light, but ensuring we have the wisdom to wield such power. Only then will we be worthy of becoming an interstellar civilization. That concludes our journey for today. I wish you all beautiful dreams and a wonderful day ahead. Until next time.